And our routine check, please say something.
Hey, can you hear me?
Yes, we can hear you, and click something.
Right.
So, not yet, not yet. We need slides to be synchronized with our big screen so everyone can see them. Yeah, click one more time. Okay, the stage is yours. Enjoy.
Hello, everybody. Thanks for joining the session today. So this is PostgreSQL, a journey from 0 to 40 terabytes in 4 years. So the agenda today is quite simple. I'll start talking about mistakes we've made as ops and how we fix them, and then I'll talk about mistakes we've made as devs and how we fix them. So remember, a platform works best when dev and ops works hand in hand together and in peace. So about me. So first, I must admit, I'm not a DBA. So I don't know all the PG's internal, and reading a query execution plan without the help of the internet is a challenge. And I'm not even a database reliability engineer, and stuff like orchestrating a PG failover gives me a hard time. I'm an SRE that comes from a software engineering background, which means that in addition to PG, I had to deal with the RabbitMQ, Redis, Google Cloud, Kubernetes. But when it comes to PG, I do manage this. So this is a pie chart where each color is a PG cluster and each outer cell is a PG table. So some clusters are bigger than 15 terabytes and some tables are bigger than 5 terabytes. So it's quite some data, and that's before replication. So I do have some experience with Postgres. But before that, I need to explain what is it that we do at Gorgias. So here comes a very short sales pitch. So at Gorgias, we build an integrated help desk for e-commerce. It means we build a software that helps our customers manage their relations with their customer. So in a nutshell, we provide supercharged mailbox for online merchants, and we do it with a software as a service subscription model. That's it for the sales pitch. So now I will explain our technical architecture and its evolution throughout the years. So in the beginning, we started with nothing fancy. Python as the programming language, Flask as the web framework, and a single Postgres server as the database. And that got us to maybe a few hundred customers and 200 gigabytes of data. Then, as the product developed, we started to add analytics kind of SQL queries to add statistics and reporting feature in the product. And as you know, those kind of queries, they are they are essentially large sequential scan of entire tables. So they hit the disk pretty hard and they trash the OS page cache. So we added PG read-only replica. All right, I've lost the slides here, but that's fine, I'll follow here. So we added one PG read-only replica. And then we added more features, such as full-text search. As you know, searching across thousands of messages across all those mailboxes is expensive. So what we did is we added more PG read-only replicas. I still don't have my notes here. All right. And that got us to maybe 1,000 customers and 2 terabytes of data. But at that time, we were onboarding a lot of customers, and the amount of data grew very fast. So we knew that this simple architecture wouldn't last long. So we changed it to the following architecture. So what we did was essentially get our simple architecture, and we started to duplicating it in several cloud regions. So each shard has its own Postgres cluster and serves a fraction of our customers. we use DNS-based routing to route each customer to its allocated shard. When a shard gets bigger than 2 terabytes, then we create a new shard and new customers sign up on the new shard. And we now have 8 production shards across 3 continents. And they range from 1 terabyte of data to 15 terabytes of data. The latest refinement we did to one-shard architecture is the introduction of Elasticsearch to do full-text search instead of PG. So how did we introduce Elasticsearch? So we wanted to keep Postgres as the single source of truth. That's because we don't trust Elastic as much as we trust PG. So we wanted to be able to rebuild Elastic data using Postgres data. Also, we wanted to avoid dual writing because managing transactions across 2 systems is hard. So we really wanted to have dual writing. So we did that with an approach called CDC for change data capture. And we introduced a software called Debezium. So Debezium subscribes to a set of changes, to all the changes that happen to a set of tables, to a set of Postgres table, using logical replication. And then it projects the data into Elasticsearch. So now the app writes into PG, but it reads from Elasticsearch. So there might be a small delay between the time when the app writes and the search is available, but that's not a big issue because usually the delay is rather small and we don't need real-time latency for this kind of workload. All right, that sums up the evolution of the architecture in the last few years. I will now talk about the challenges we've faced along the roads, and how we fixed them, and especially around dealing with multi-terabyte clusters and multi-terabyte table. All right. The first issue I would like to mention is PG connection in the idle in transaction state. So maybe as you know, Postgres uses a process-based concurrency model, which means each time there is a new connection to Postgres, there is a process fork happening. And that new process is entirely dedicated to handling this new connection. That's why it's best to limit the amount of maximum connections to PG to reduce the CPU context switches, among other things. But our apps, we have many apps connected to Postgres, and they need thousands of PG connections. So we introduced a connection multiplexer, which is called PG Bouncer. So PG Bouncer uses an event loop to efficiently handle thousands of client connections. And the good thing with PG Bouncer is that the same connection can be reused by multiple clients. But the same connection cannot always be reused, especially if the transaction is in the middle of a transaction. That's why we can't have long-running transactions, because otherwise we can quickly run into the situation where we don't have any connections available in the connection pool. So really, long-running transaction or client that disconnect before committing or rollbacking transaction is a major source of issue. So this idling transaction typically happen with the following pattern and situation. So a client would start a transaction with the begin statement. Then it would do a big select on a big table that returns a lot of rows. And then for each row, it would do some heavy processing, maybe an external very slow network call. And at the very end, it would commit the transaction. We can quickly imagine that this transaction is going to take a long time, especially if a lot of rows are returned. And that most of the time, the transaction will be idling, meaning Postgres will wait on the client to process those messages. So that's how it happens, typically idling transaction. What are the solutions to this problem? So you would think that the app should be changed because it looks like it's an application bug. You would be right, but fixing this is not so easy. First, the application could be very big with many places to fix. Also, the place where the transaction starts, the processing is done, and the transaction ends could be at different stack frame, different functions, so that makes the whole pattern here less obvious. Also, the use of ORM, such as SQL Alchemy in Python or Active Record in Ruby, it abstracts the transaction lifecycle and transaction management, which makes it sometimes a bit hard to know when the code is actually executing in a transaction. And finally, less experienced developers or developers coming from another database, such as MySQL, they are simply not aware of this problem. So we fixed it for good at Gorgias with the idle in transaction session timeout parameter. And this parameter will cancel any transaction that has been running for more than this amount of time. So this parameter can be set globally, so using the PostgreSQL.conf global file, or on a per user or per database basis. So it's pretty flexible, and I really encourage you do the same in your production system. The next issue I would like to talk about is vacuuming large table. So vacuum is a maintenance operation that removes dead row from the table and index files. So dead rows are rows that are not visible to any transaction. Dead rows are produced by delete or update statement. We have to remember that with Postgres, an update statement actually creates a copy of the row, and the old version of the row will be deleted by the vacuum. So vacuum is critical to maintain consistent query performance. It operates in 3 phases. The first phase is a scan of the entire table where dead rows are searched and their location is put in an in-memory buffer. The second phase is the indexes cleanup, where elements that point to dead rows, elements of the index, are actually deleted. And then the last step is the cleanup of the table, where the actual rows are deleted from the table file. When it comes to dealing with large table, the general advice with vacuum is that it's better to pay a little frequently than a lot later on. That means you want to run vacuum more often. But to run it more often, it has to be fast, otherwise it never completes. There's a couple of levers we can pull to deal with the vacuum of large table. The first one is the vacuum scale factor. So that's the percent of dead rows that needs to be in a table before the vacuum kicks in. The default value is 20%, which is quite high. And imagine you have a table with 1 billion rows, then the vacuum will kick in when 200 million rows are considered to be dead, which is quite a lot of dead rows, and it can impact the performance. That's why the first advice would be to reduce the vacuum scale factor to maybe 2% of dead rows. The second parameter is the vacuum cost delay. So the cost delay is basically a sleeping time, a wait time that vacuum does in order to not hit the disk too much, so to make it go slower. But what you want to do with large table is to reduce the cost delay. So that makes the vacuum a bit more aggressive, but you have to do it in order to make it faster. And also one thing to remember with Postgres is that the default values are usually rather conservative. So it's fine to reduce here the cost delay. The third parameter is the maintenance work mem. The maintenance work mem is the size of the shared buffer, the buffer, the memory buffer we've discussed before. It's important that this memory buffer can hold the location of all the dead rows, because if the buffer is too small, then the second phase of the vacuum, which is the cleanup indexes, if the buffer is too small, this step will have to be performed in several passes, which means the indexes will be scanned several times. And if you have big tables, you will have big indexes. So scanning those indexes in several passes is bad. So you want the maintenance work mem to be large enough. The last parameter is that you can tweak is the parallel maintenance workers. So that's simply the number of workers that will process the indexes in parallel in step 2. The step 2 of vacuum is essentially the only operation that can be performed in parallel. Each index can be cleaned up independently. The last advice is to proactively run vacuum at night. And here the rationale is that given that vacuum hits the disk pretty hard, it's better to do it at night during low time if you have such low time. But in our case, even after tuning all this, we still observed hours-long vacuum on some of our largest tables. So we resorted to the bazooka, which is table partitioning. And the rationale is the first and the last step of vacuum are essentially large sequential scan of the entire table. So the smaller the table is, the faster vacuum is. So that's why partitioning helps. I call it the bazooka because partitioning a live table with a lot of rows is not trivial. And also partition maintenance is not really straightforward. So I would only recommend partitioning if one of your table gets maybe bigger than 1 terabyte. So how did we partition at Gorgias? So remember, each shard hosts the data for thousands of customers. And because we are a multi-tenant app, all of our tables have a merchant ID, customer ID column. So we decided to partition on the hash of merchant ID, modulo 128, to have 128 partition. Yep, sorry. So we wanted to have all the partitions of approximately the same size in order to avoid hotspots, and we wanted to have most queries visit a single partition. That's key decision to make. Don't go too high with the number of partitions, because if you have queries that visit many partitions, then the query planner will go a bit crazy and the CPU usage will be quite high, even for simple query. Next thing I would like to explain is how we did the live partitioning of such big table in production. So this time again, we used Debezium and logical replication. But this time, instead of projecting the data into Elasticsearch, we projected the data into the newly partitioned table. And what's good about this approach is that it doesn't require any code change. It's totally transparent to the application. And then once the two copies were in sync, we did a table swap. which is basically a table rename. We had to actually wait for a maintenance to rename the table, because renaming a table requires an expensive lock, so it's an access exclusive lock, and this kind of lock prevents any reading and any writing on the entire table. And if you have a busy table, well, there's always some traffic. But we have maintenance windows every 3 months, so we just waited for the next maintenance window. That brings me to our next issue, which is PG locks. So there are 8 kinds of table level locks. Some are rather lightweight, such as the access share lock that is taken when a row is read. And some are very heavy locks, such as the access exclusive lock, which prevents any read and write on a table. And even for a series, it's hard to remember which command acquires which kind of lock. And for instance, at Gorgias, we learned the hard way that the reindex command, even with the concurrently option, block vacuum. And you really don't want to block vacuum. And then, in addition, devs, they regularly have to make DB schema changes with the alter table statement. But the doc for this alter table statement is not very clear on to which kind of locks get acquired by each of its different forms. You can see here the alter table command is rather complicated. It has many forms, and each form could acquire a different kind of lock. So navigating this is not trivial. And the doc doesn't either kind of hint on whether a given form, a given alter table statement is safe to apply in production. So some recipes are considered safe, so not too much locking. Some are well known, such as creating or deleting an index with the concurrently option. That's rather safe. Or you can add a not null column if it has a default value. That's okay, that's fine. Some other recipes are safe, but not so well known. For instance, if you want to have a foreign key constraint, then it's better to do it in 2 steps. First, you add the foreign key constraint, but you mark it as not valid. And then, in a second step, you validate the constraint. That's how you minimize the amount of exclusive lock that is taking on a table. So what are solutions to this problem? So you would think that there must exist some linter that would scan the migration file and tell you, hey, this migration is potentially dangerous because it acquires some heavy lock. But we couldn't find one, a linter, readily available. I think that's because there are many programming languages and many migration tools, so it's hard to come up with a generic one. So my guess is that each team has developed some in-house custom solution. So at Gorgias, we had to resort to teaching and code reviews. But that's not enough. There's one problem. The main problem is that if a query waits to acquire a lock, an expensive lock, even if it's just waiting to acquire the lock, so it's not holding the lock, just this query waiting can block any following queries. And that's because the queries will be put in the same queue as the query waiting to acquire the lock. So really, sometimes just waiting to acquire a lock is enough to lock an entire table. So we've prevented this by running all our migration file, all our DB schema changes with the lock timeout value set to 10 seconds. And what this parameter does is that it will cancel any query that is waiting for a lock for more than 10 seconds. So it means that potentially our migration operation will be canceled and we will have to retry them later, but at least they won't block reading and writing on the table for more than 10 seconds. And you can set this parameter, log timeout, either with the set session command or with the PG options environment variable if your driver understands this env variable. All right. Next issue is forced checkpoints. But again, what checkpoints are? So as a reminder, any change in Postgres will be first written to a WAL file. And then Postgres will update its in-memory data structures in a zone called the shared buffer, but it will not write those changes in the data file just now. It will do it later. And this is to save some IOPS operation and speed up things. But the problem is the WAL file can get big. And it can actually get bigger faster than the actual data file. And why is that? Imagine you have a lot of update statements. Then the WAL file will grow, but the data file might not grow as fast. So to limit the growth of the WAL file, Postgres will periodically flush all the dirty buffers. So that's the buffers that are in memory and that have not been saved to disk yet. So those dirty buffers will be periodically flushed to disk and saved. And then PG will be able to recycle the WAL file because PG will know now that it can reconstruct the data using the data file and it doesn't need the WAL file anymore. So it can recycle the WAL file. Right, a forced checkpoint is a checkpoint that happens because the WAL file gets too big. And it creates a big I/O spike. A forced checkpoint creates a big I/O spike because all of a sudden there is a lot of stuff to write to disk. And more importantly, it prevents the ability to squash and merge some IOPS. What do I mean by that? All right, let's take a look at this diagram. Here, we have 3 SQL statements between 2 checkpoints. The checkpoint timeout here is set as 5 minutes. And we can see that the result of those 3 statements is that in the end, there is nothing to write to the data file. And why is that? That's because the last statement, the delete statement, will cancel the previous 2. So in the end, there's nothing to write to the data file. So in a way, we've saved some I/O operation, and that's good. We can see here that the longer the checkpoint timeout is, the more opportunities there are to save some IOPS. But the problem, again, if you have a long checkpoint timeout, the WAL file will get big. And bigger WAL file means longer recovery time. And that's because if PG crashes, it has to go over all the WAL file and reprocess the rows. So you don't want to have too big WAL file. And now I'll explain how to properly tweak the checkpoint behavior and the checkpointer. There are, as we discussed, 2 main parameters, the checkpoint timeout and the maximum WAL size. So let's see how to properly tweak this. So what I recommend doing first is to increase the checkpoint timeout from the default, which is 5 minutes, to 15 minutes. Again, I think Postgres default parameter are rather conservative, so it's rather safe to increase that, to try to increase that to 15 minutes. Then the next thing you want to do is measure how much the WAL grew within these 15 minutes. So what you can do is just measure the size of the WAL, wait 15 minutes, and then measure the size of the WAL again, the WAL file, and then you compute the difference, and that should give you the growth of the WAL file. So in this example, so I gave you the command to do that, but in this example, the WAL file grew by 3 GB in 15 minutes. So we are setting this 3 GB as the max wall size, and then we add some margin of safety. And once you've set this parameter, you want to measure how much it impacts the recovery time. So to do that, what you can do is forcefully kill Postgres. So maybe with you send it the kill signal to kill it hard, and then you restart Postgres, and you look at the log, and you try to figure how long it took to recover. So in this example, it took less than 1 second to recover, so that's fine. But for instance, on some of our production systems, we have max wall size set to 16 or 32 GB, and it can take 10 minutes to recover. So if you think the recovery time is too long, then you might want to reduce both the checkpoint timeout and the max wall size. All right, next issue I would like to talk about is large JSONB columns. JSONB type is great. It's fast enough. You have a lot of PG functions to deal with JSON document, PG functions, PG operators. You get, of course, schema flexibility, and it eases the interfacing with external system that could also talk JSON. So you also have like indexing with the expression index, and you also have integrity constraint for JSONB columns. So they are really first-class citizen in Postgres JSONB. So that's great. So in a way, PG could feel like a document store with ACID guarantees, but there are a couple of caveats with those JSONB columns. The first one is that you don't get column statistics with JSONB. So for other data types, Postgres computes some statistics on the distribution of the values for this column. So statistics such as the percentage of null values or the most common values. And those statistics help the query planner make the best decision on how to execute a query. So the absence of column statistics for JSONB means that the query planner could take suboptimal decision, and that could lead to slow query. The other downside of JSONB is their large storage footprint. So imagine you have 1 million documents and they all share a common set of keys. Then you're going to duplicate the key names. And if you have millions of documents, that could be expensive. And the other downside has to do with how Postgres deals with large values. We have to remember that Postgres used fixed size pages of typically 8 kilobytes. And Postgres does not allow a single row to span multiple pages, which means it's not possible to store directly values larger than a few kilobytes. To overcome this limitation, PG has two main options. It can either compress the value, or it can split the big value into chunks, into fragments. And those fragments are not stored in the table directly. They are stored in a companion table, which is called the toast table. And in the regular table, only pointers to the toast table will be stored where the row would usually be. So there is a level of indirection. And this out-of-line storage suffers from two main limitations. First one, it doesn't allow for partial updates, which means that even if you have a big document, big JSON document, maybe 1 megabyte, and you only want to update a few bytes, you use very selective operator to just rewrite a few bytes, but in the end, Postgres will still have to rewrite the entire document. And the same goes with partial read. You cannot read only a small part of the entire document. Even if you want to read just a single key, Postgres will have to fetch and read from the disk the entire document. So JSONB are expensive. All right, quickly, running PG in Kubernetes. So we've been running PG in Kubernetes since the beginning at Gorgias. In the early days of Kubernetes, it was not recommended to run stateful workloads on Kubernetes, but nowadays it's pretty straightforward. So in terms of setup, we run one stateful set for the PG primary with exactly one replica, of course, and we run one Kubernetes stateful set for the PG hot standbys with many replicas. And, all right, each container, when it starts, it has an init script that sets up the replication, whether it's the primary or the hot standbys. So that's the init script. In terms of pros and cons, pros, spinning up a new replica is trivial. It's just a single command. Kubernetes will create the container, create the disk, add the container in the load balancer. Easy. A lot of goodies come from free with Kubernetes. You get auto restart. If PG crashes, if the host, so the server crashes, Kubernetes will just recreate it. You have cloud, you can tell Kubernetes to spread your different replicas across AZ, so that's good for high availability. And you benefit from the entire Kubernetes ecosystem. In terms of cons, well, if you need custom PG extensions, you'll have to create your own Docker file, so that's a bit more maintenance. If you do some kernel tuning, such as if you disable transparent huge pages, or if you want to have explicit transparent huge pages, then the solution is a bit hacky. That's because with Kubernetes, you're not supposed to tweak the host kernel so much. And finally, I would say that Postgres is not a cloud-native app. It means that there will only ever be one single PG primary container. That's how PG works. So we will always have to pay attention to this special container. And that goes a bit against the philosophy of Kubernetes, which is to manage cattle containers and not pet containers. And for instance, at Gorgias, now we dedicate entire VM, virtual machine, to run just each of the PG container. And those PG container, they run on a dedicated node pool alone, because we wanted to have special hardware and we wanted to avoid the noisy neighbor phenomenon. That's it in terms of conclusion. So Postgres is a very versatile database. It can scale quite easily as your business grows. And if you're fortunate enough to be very successful, then you have options. In this talk, we've discussed about 3 options. First one, re-architecturing via the introduction of shards. Second one, specialized data stores, such as Elasticsearch. And the last option we discussed is the native PG partitioning. We did the last 2 approach option using CDC, Change Data Capture, and Debezium, and I strongly encourage you to look into CDC if you manage data at scale. That's it for me. Well, if you have questions, I guess now is the best time.
Thank you, and thank you for bearing this technical issue. I really didn't see that they are not doubled here. Thank you for using these screens. That was amazing. Okay, and now we have our 15 minutes Q&A section. How it feels to handle 40 terabytes with Postgres. And our first question to the left, please.
Hello. Thank you for your presentations. It was very interesting. My name is Sergey, and I have a question. Which tools are you using for monitoring and troubleshooting Postgres?
The main tool we use now is called PG Analyze. It's good. I recommend it. We are considering Datadog because they've recently launched a database monitoring solution. We have not looked into it yet. But it's mostly PG Analyze, and we have a couple of custom dashboards in Datadog via their Postgres integration. So Datadog and PG Analyze, and sometimes we connect directly to the server and we look at the PG stat statement view. But that's a bit old school, but sometimes we do that.
Okay, next one to the right. Please allow me to provide you a microphone. Your microphone, please.
Yeah, thank you for your presentation. I'd like to ask how much data do you recommend to store on one shard based on your experience, and also about the vacuum. You told that you need some extra space to do the vacuum, to buffer some
Yeah,
so
maintenance work mem.
how many space in maybe like percent do you recommend also to have on disk? Thank you.
First question. So now we create a new shard each time a shard reaches 2 terabytes of data. Postgres is fine with more than that, but we have to account for the growth of the customers that are already in the existing shard. So we close the shard at 2 terabytes, and then the shard will increase naturally. But as I said, we have shards with 15 terabytes of data. I don't recommend it, it's too much, but anything between 2 and 6 terabytes doesn't give us trouble. But the biggest problem is, I would say, is the biggest table. So if you have like 10 terabytes of data but spread across 100 tables, that's fine. But if you have like only 5 terabytes on a single table, that's trickier. That's the first question. And in terms of vacuum, so I think maintenance work mem is set as currently in prod. Even for our biggest system, it's 1 or 2 gigabytes. If it's too low, you will see in the logs that the index cleanup phase operates in several passes. So if you see logs that say, yeah, the index cleanup happened in several passes, that's no good. You want to increase the maintenance work mem.
From the conference from outside and a conference from inside, they look completely different, actually. Right now, you're enjoying the talk, the Postgres, amazing speaker explaining everything. But in the middle of the talk, inside, slides that he see, they just disappear, like no slides. So it just due to his amazing skills that he use big screens in order to continue the talk, and everything just fine. But from the inside, it's kind of broken. And right now, I'm thinking what safeguards to put in place in order for follow speakers. And next days, they always have the slides visible to them. Okay, that was some small talk. Please, you're welcome.
Jordan, thanks for presentation. 2 questions. The first about do you have and use some high availability software like a Patroni or Async pacemaker for your infrastructure Postgres? And second question about vacuum every night as a correct. Maybe you can replace just vacuum on PG compatible or PG repack or something. Thanks.
Can you repeat just the second questions?
Second question,
yeah.
About vacuum, you use every night, as I understand you correctly.
Yes.
For each shard.
Yes.
For each table.
Yes.
Maybe you can
use PG repack.
Yeah, but PG repack, as I remember, need extra more spaces, but PG compatible from data egret, as I remember correct.
Yeah. Right, I got it.
Did not need some extra spaces.
Yeah, got it. So first question, whether we use some high availability software like Patroni. So I must admit we don't. We don't. And why is that? So we are actually running 8 production clusters, and we've been doing that for years. And it has been our experience that with Google Cloud, the servers don't crash too much. Maybe we got lucky. I mean, I can only recall of 2 PG primary crashes across in 5 years, and when they crash, they restart in 10 minutes. So by the time we get paged, because we are on call, by the time we get paged, then the database is already up and running. So we don't feel, it's a bit strange, but we don't need the field to have a highly available software such as Patroni just yet. Second question about PGRepack. So for years, we've heard some scary stuff with PGRepack. I mean, back in the days, I think it was not ready, production ready, or there were some quirks. So we didn't try it. I know that recently it's good, it's production ready, no one has reported issues, but I'm still a bit scared about using PGRepack right now. And the extra space is an issue because we have tables, multi-terabyte tables. So if you need to make a copy of that table, it's multi-terabyte of SSDs, and you know SSDs in the cloud, they are crazy expensive, so we really have to pay attention to SSD space.
I almost forgot, due to the slightest issue, you will need to name the best question. So please start to arrange them from now on. And next question.
Thanks for presentation. And why don't you split user data for more small tables by tenant ID, for example, for avoid so big tables? Thanks.
But I think that's what we are doing. We are now partitioning our biggest table on the hash of the merchant ID. And we are doing that for most of our biggest tables now. So is that... So yeah, that's what we are doing now. We are partitioning based on the customer ID column.
We have a time budget for 2 more questions. After that, you will be able to take speaker to our communication zone where you will discuss everything. Please.
Yeah, hi, thank you for your presentation. And you have 40 terabytes of data, and I might guess that not... What portion of the data is indexes, actually?
Is in where?
What portion of the data
indexes?
are indexes?
Oh, that's a very good question. It's a lot.
It's just a part of a question. I mean, I can guess that not all of your indexes, even not all of the hotspot indexes, fit into
in RAM.
memory.
You're right.
Yeah. How much of a problem is it? Have you experienced any severe issues with that, especially when you have spikes in read throughput or write throughput? And how do you deal with it?
So that's an excellent question. The indexes are massive. So I would say they amount for 1/3 of the total database size. So the indexes are massive. They don't fit in RAM, but we do have a lot of RAM. For instance, for our biggest server has 15 terabytes of data, but it has 1.5 terabyte of RAM. And as I said, the indexes are 30% of the total size. So back to your question, we haven't looked into this problem, which kind of means that maybe it's not a big problem, maybe it's a problem, but we are not aware of it.
One more question from the right part. The person here is waiting for a long time, so this will be a final question. Please, you're welcome.
Thanks, Jordan, for the presentation. A little question, maybe based on your experience. When tweaking the amount of shared buffers to give the Postgres ability to cache the shared data in memory, did you usually follow the traditional recommendation of like 25 to 35% of all RAM available, or maybe it's sometimes more efficient to minimize the shared buffers and let the operating system take care of caching more efficiently?
Yeah, so I've heard about that. For now, we've stick to the 20% rule. There is a good blog post by PG Analyze guys that went out recently, and even the EDB consulting company did some research. I think we have to make our own research too, because it's highly dependent on the workload. But experimenting with that, performance testing, load testing, it's complicated. It takes a lot of time. You need to replicate the production workload on a copy. It's hard. So we haven't really looked into it. We've stick with the 20% default.
Mm-hmm. So, a round of applause, please, to our speaker. And now the social thing, which question deserves this something?
I think the gentleman who asked 2 questions, there were 2 good questions, so I think you...
Please come to the stage, and it's your role to gift this gift. Applause, please.